Hello everyone, my name is Naveen, and today I'm going to be talking to you guys about location services. So let's get started. So before I get into the meat of the topics, I'm going to give you an outline of what we're going to be talking about today. We're going to start off by discussing what exactly a location service is. Once we understand what a location service exactly is, we're going to go on to discuss the fundamental technologies underlying how location data is determined. We're going to start off by talking about the Global Positioning System, abbreviated as GPS. Then we're going to talk about cell tower trilateration. Then we're going to discuss IP address-based geolocation. Finally, we'll discuss Wi-Fi-based positioning systems. With an understanding of various positioning techniques, we'll talk about how we can combine them to get more accurate results in location data. Specifically, we'll talk about how we can extend GPS technology with Wi-Fi. With a good understanding of the technologies and how they work cohesively, we'll talk about how to actually create a location service. In this section, we'll discuss the wonderful abstractions that operating system vendors have provided to us in order to make our lives a lot easier when building location services. After understanding how they're built, we'll talk about the current applications of location services in day-to-day life and how they benefit mankind as a whole. So, what exactly is a location services? As you all know, computing technology has dramatically altered the way us humans communicate. Just a couple of decades ago, to send a message a few hundred kilometers, it would have taken days, whereas now it takes a matter of milliseconds. Ever since the inception of ARPANET, the predecessor to the internet in the 1970s, computer networking has seen rapid advancements in research and development. Alongside the networking advancements were satellite technology advancements, and both played a critical role in pioneering geographic data collection. Location-based services can be described as software services which utilize geographic data and information to provide services or information to various users. To get the location data that's leveraged by these location services, various technologies need to be used. These include GPS, Wi-Fi, IP address mapping, cellular signals, and much more. Satellite technology, however, was the fundamental technology that helped spark the mind of the one who pioneered GPS, one of the first positioning systems to exist. So, how was GPS inspired? Well, to understand that, we need to talk about the first ever satellite launched. The first ever artificial satellite launched was called Sputnik 1, and it was launched by the Russians in 1957 as a part of a series of technological developments during the Cold War. It had 4 radio antennas and 2 transmitters, broadcasting a distinctive beep beep sound as radio waves. Back on Earth, William Guyer and George Weifenbach at the Johns Hopkins Applied Physics Laboratory set up a receiver to listen for this signal. They noticed the signal varied slightly in frequency every time they checked for it, and this was due to its Doppler effect. With the Doppler shift, Sputnik's position relative to the receiver could be determined. Reversing this technique, we could use satellite orbits and their Doppler shifts to determine a receiver's position. Realizing this possibility, both of them outlined what would become the first transit navigational system. So, the first ever system. What was it? In the 1960s, the United States Navy utilized 6 different satellites to track submarines carrying nuclear missiles, within a precision of a few minutes. And after collecting the data from the submarine tracking experiments, the Department of Defense wanted a more secure and stable system in place, and so they set out to build that system. The system was launched in 1978 and was called the Navigational System with Timing and Ranging. It was abbreviated as the Navstar. The system, however, only became fully operational with a total of 24 satellites in 1993. This system was the first ever global satellite-based tracking system, and eventually led on to become what we know today as GPS. So, what is GPS? You hear about it, you know you use it every day. Everyone's phone has a receiver. We use it for simple tasks like finding bus routes, finding tracks. But what does it? How does it work? What's behind this technology? So let's describe GPS a little bit. It's a system that's owned and maintained by the United States government and Air Force respectively. It consists of at least 30 satellites orbiting the Earth at any given time. The GPS system may have more than 30 satellites, but only 30 are guaranteed to be active at any given time. This is because we need that many satellites to guarantee a certain rule. So the orbits of satellites are actually controlled algorithmically on a ground station in such a way that anywhere on the Earth, 4 satellites will always be in view. All the satellites send out signals all in sync at periodic intervals. GPS receivers are non-expensive pieces of hardware that are installed on many smart devices, and these receivers are responsible for processing the signals from the 4 available satellites and determining the location of a given node. The knowledge of the speed of radio waves, the speed of light, the Doppler effect, this together creates an opening for a technique called trilateration, which is primarily used to determine the location. So, as we said in the earlier section, GPS sends out radio waves in periodic intervals all in sync, all the satellites at the same time. Now, GPS actually, to be specific, they send out 2 types of signals. The first is a standard positioning service, abbreviated as SPS. The signal is built off a level 1 carrier frequency at 1575.42 MHz. This is a signal band that we consume for our daily GPS use. It's available continuous on a worldwide basis, and it's free of any charge. GPS receivers that are created to date can process SPS signals and decode them very easily to extract the navigational data that's coming from them. The second type of signal is called the Precise Positioning Service, abbreviated as PPS. The signal is built off a level 2 carrier frequency at 1227.6 MHz, and it's restricted to select US government organizations. It's actually used for highly accurate military positioning. Both signals contain precision code ranging. However, with PPS, the navigational data message is encrypted for reserved authorized users, and only those users with the decryption key can actually decode these messages and understand what's behind them. So, let's talk about trilateration specifically. It's an important concept that's actually going to apply across a lot of our different positioning techniques. So, what is it? It's a method that's used to determine the location of a point using multiple distance between that point and known positions. So let's say you have a smartphone, right? It has a GPS receiver and it has the ability to interpret various GPS satellites. So let's just say we have, as in the diagram, we have satellite 1, and we could say it's about 12 kilometers from you. The blue circle representing it shows all points along where you could be. Now, let's just say after this, you come to know that satellite 2 is 15 kilometers away from you. Now you can see that for the math to be correct, the location can be anywhere along one of the 2 points the blue and the orange circle intersect. Finally, if we come to know the position of a third satellite, say satellite 3, which is 10 kilometers from you, all 3 circles intersect at a single point. At this point, you can identify the location of a receiver as the point where all 3 intersect. This essentially sums up how trilateration works. So, let's talk about GPS-specific trilateration. As you all know, as I described earlier, trilateration is a primary mathematical technique that's used to calculate the location of a device with a GPS receiver. To do this trilateration, a device with a processing unit needs to know the location of at least 3 GPS signals and the distance between the device and each of those satellites. GPS receivers analyze the SPS radio waves coming from the satellites. With the knowledge that radio waves travel at the speed of light, the receivers can determine the distance to the satellite looking at how long it took the signal to arrive from the predetermined time it was sent. Additionally encoded into the SPS signals are positions of satellites that are sending them. This way, we have both pieces of information. In most implementations, however, GPS receivers look for 4 or even more satellites to better improve their accuracy. Some devices even have multiple GPS receivers to pick up signals simultaneously. However, with GPS trilaterations, accuracy deficiencies can occur when clock timings are mismatched. Satellites use atomic clocks to be perfectly in sync. However, due to their expensive nature, receivers can only use regular quartz clocks. To address these precision problems, more than 3 signals can help. But additionally, the clock of the receiver resets constantly based on the incoming radio waves from the satellites that have the synchronized clocks, the atomic clocks. Next up, we're going to talk about cell tower trilateration. So it works very similarly. You know, we need 3 points, we need to determine the intersection, and that's why you find the node. But the communication and signaling mechanisms are different. So some devices that require location services may not even have a GPS receiver. However, older devices in all these cases have cellular transmitters and receivers. A device doesn't need to connect to a cell tower. As long as it can receive a signal, the location can be determined. And a cell phone is constantly emitting radio signals that can be picked up by cell towers within the vicinity. And if they're picked up by at least 3 cell towers, trilateration can work. When the signals are picked up by cell towers from a cell phone or something with a cellular transmitter, the distance can be estimated using either the signal strength as an indicator or by measuring the signal time delay between the towers and the device. This technique benefits older devices that don't have any GPS hardware on board. The downfall, however, is the lack of accuracy globally. In urban areas, cell towers are much more densely packed together, which provides locations with precise trilateration. However, in more rural areas, where the density of cell towers is low and maybe even non-existent, trilateration doesn't provide a very accurate location results. Contrasting this, GPS is a mesh of satellites that guarantees availability algorithmically anywhere on the surface of the Earth. The next positioning technology we're going to talk about is Wi-Fi based positioning systems. And like the last two, it's very, very similar in the way it works. So Wi-Fi signals, as you know, are being constantly emitted from various access points. And with the way technology is evolving, there's thousands and thousands of access points from any given location in urban areas. And Wi-Fi shows very good promise over GPS in indoor settings because GPS signals are harder to penetrate indoors and they get skewed when they are measured from indoor setting. Whereas Wi-Fi signals are mostly coming from indoor settings and indoor access points. So they work in a very similar method to GPS and cell towers, as I said, in the sense that they have the inherent challenge of determining the position of a client with respect to various access points. Wi-Fi positioning systems employ a multitude of techniques to determine the distance from an access point. One of these techniques is called the Received Signal Strength Indicator, abbreviated as the RSSI. This indicator is a measurement of the power present in a signal. Based on the RSSI, a node can map a distance to a signal. Along with RSSI, the SSID of the Wi-Fi hotspot and MAC address are used to determine the location of that specific hotspot. Another technique for measuring is called the time of flight, or abbreviated as a TOF. This technique is done by measuring the amount of time a signal took to be received by a node. Using this time, the distance can be estimated because we know the speed of a signal. Although the technique is the same, Wi-Fi positioning prevails indoors due to just the nature of much stronger and precise signals. The final positioning technique we're going to be talking about today is IP address based geolocation. So, when connecting to the internet service providers assign a public IP address to a connecting network. Public IP addresses are limited, and therefore the various address ranges are assigned to various ISPs by the Internet Assigned Numbers Authority, also known as INAU. With the given range, ISPs normally split the ranges into subranges that are location dependent. Whenever a node connects to an ISP, an IP address from the pool for that given location is assigned. The mappings of IP addresses to average location areas is publicly available, and therefore it can be queried for a location when a node knows its own IP address. It's important to note that IP address based location can only give a rough area of where a node is. It can't give any more granular information. It can never be 100% precise. This is because the addresses are usually being shuffled between various users every time a user connects and disconnects. However, the benefit with IP-based geolocation is that it's very low cost, if not nothing, and it requires literally no user consent because we're just querying a publicly available database for this information of mappings of public address to physical geographic address. So we've talked about GPS, we've talked about cell tower trilateration, we've talked about Wi-Fi based positioning and IP address based mappings. Now, these are individual technologies and they work on whatever devices have the hardware to support them. But how can they work together? Let's talk about how we can extend GPS with Wi-Fi. So, as you all know, GPS is the superior technology outdoors. Indoors, GPS signals are very weak and they can't penetrate through hard cement, hard settings, various floors, underground settings, and whereas Wi-Fi signals can. So, given the close proximity of Wi-Fi signals, we get more accurate location data and they're clustered much closer together. So, with both GPS and Wi Fi hardware on board, how these two technologies work in cohesion is that GPS is initially used to get the current position of a given node. Once GPS location determines where a node is, the node goes on to access various access points and determine where they're positioned and send that information back to the GPS company. This way, next time somebody connects and has a weak GPS signal, they can use the previously mapped database to determine Wi-Fi hotspots, their locations, and estimate a given node's location based off of this table of access point collections. So like this, various positioning techniques can be used in tangent to get more accurate results when certain resources are lacking. So we understand these techniques, we know how to put them together. Let's talk about creating location service. The funny thing is, we don't need to know about half of this stuff when actually writing a location service. Most of the operating system vendors have done the thinking for us. Most OS vendors provide us with APIs and SDKs written through operating system level system calls. They've taken away all the confusion of dealing with various pieces of hardware and just given us very simple APIs to develop against. Now, the disadvantage here is that we don't get to pick what hardware we're using, but we also get to very easily develop for location services. So, various APIs include Core Location for iOS and macOS. Google Location Services API is supported for Android. On Windows systems, when doing any sort of .NET or C# based programming, there's the Win32 Location API. And for web, there's actually something called the Geolocation Web API, very well described in the MDN docs. So like this, we have very simple interfaces to get location data, but behind the interfaces, the controller is figuring out what hardware is on board and using this hardwares in cohesion to get the most accurate result given the current circumstances. So, various applications of these location-based technologies include mapping services like Apple Maps and Google Maps, event planning services like Yelp and Eventbrite, booking services like Uber, Lyft, and Airbnb, fitness services like a jog tracker or hiking trail apps, and even dating services like Tinder, Bumble, and Hinge. Location services have really penetrated our market and really have changed the way we live our day-to-day lives. And the honest truth is, it really does. The limit of what we can create really just comes down to what we can think of. So that was an overall summary of how location services work. At the end of the day, it's as a software developer, we just need to understand how to interface with this. But fundamentally, there's some various hardware components that are helping us get this location information. So I'd like to finish off by covering what we talked about. Location services can be determined on any node depending on the hardware that's available. GPS, cellular, and Wi-Fi techniques all use trilateration, but different methods to get the data for it. GPS and Wi-Fi can be combined to make data more accurate and available when certain technologies aren't. Implementing location services doesn't require any knowledge of this hardware. It's simply abstracted by the vendors that provide us the APIs and SDKs to develop on a given platform. And like we outlined in the applications, your mind really is the limit to what you can create with this. Thank you for listening to me. Here are my references, and please feel free to contact me if you have any questions. Thank you.